Hi everyone. In this video, I want to show how we can use Logisim to implement Booth's algorithm for multiplication. So before I show you how I implement it using Logisim, let's first review how Booth's algorithm works. Right, so this is the flowchart I have for Booth's algorithm, right? And I'm sure you are already familiar with this. So what do? We have register A, where we are going to, it's also called as accumulator, right? So we're going to initialize it to 0. We have a bit q minus 1, which is also going to be initialized to 0 because this is, we are just starting out, right? And we have m, which is your multiplicand, q, which is your multiplier, and your count is n, right? So if we are trying to multiply 3 times 2, let's say, then your m, you're going to initialize it with 3, and your q, you're going to initialize with 2. A will be 0 in the beginning. Q minus 1 is a bit, so you initialize it to 0 as well. And then your count will be whatever number of bits you have in your multiplier. If you have 4 bits, your count will be 4. If you have 8 bits in Q, then your count will be 8, and so on. All right, so the first step is to initialize, and then afterwards, what you are going to do is you compare, right? As you can see here, we are going to take the Q0 bit from your Q, which is your LSB bit, right? And then Q minus 1. Since there are 2 bits, there are 4 possible combinations, right? You 0, 0, 0, 1, 1, 0, or 1, 1, right? So as you can see over here, if they are 1, 1, and 0, 0, right? So if for these two cases, you just do the arithmetic right shift for A, Q, and Q minus 1, right? So you consider them as one register, and then you arithmetic right shift by 1 bit, and then you decrement the counter and check if the counter is 0. If no, then repeat the process, right? But if the bit is 0, 1, like Q0 and Q minus 1 is 0, 1, then what do? This is the case, right? Then you add what's in A with M and then store back it in A, right? So if it's 0, 1, you add A plus M. If it's 1, 0, you do A minus M. Okay, and then for both the cases as well, you have to arithmetic right shift, decrement the counter, and then repeat the process until the counter is 0, right? So this is how the Booth algorithm works. Now let's see the same implementation in Logisim. Okay, so let me switch my computer to show you the circuit of Logisim. Okay, so I need to resolve this, clear. Okay, so here is the implementation of Logisim, and I'm going to walk through what I'm doing doing here. Okay, so in this example, I'm implementing a 4-bit. This one, the circuit is a 4-bit Booth multiplier. Okay, so what do I have? I have register M, okay, to store the 4-bit multiplicand value. I have register A to store the accumulated product, right? And in the beginning, we are going to initialize it to 0. I have a register Q to store the multiplier, right? I have another register, 1-bit register, which is a Q minus 1 to store the Q minus 1 bit, okay? And as you can see on the left, right, where you can find these registers, it's in the memory section, okay? So I'm already using the built-in components in the Logisim. Okay, so here I have register, right? So to get these registers, you just go to the memory and then get the register, right? And then you choose. So for my example, I'm using 4 bits, but if you want to build a larger, if you want to build a multiplier that multiplies large numbers, then you can choose the bits accordingly over here, okay? And then Also, you could choose whether this register is a rising edge or falling edge, high or low. So for my case, I'm just choosing it as a rising edge, right? And so as you can see here, this register is going to take in, like, let me just put it over here and show you, right? So I can just pull the components from over here and add it into my workspace. And as you can see here, it has like the D, which is going to be the input. Q is going to be the output of this register. And then along with these two input output, it also requires the enable line, and also it requires the clock. Okay, so whenever the clock rises, whatever is stored in the register can be seen in the output line. Okay, so that's how the registers you're going to use. All right. So that's why you can see here I have, and again, when I'm running the circuit, I will make this enable line as 1, and then I have also supplied the clock, right, for all of them. As you can see over here, all of them is getting this clock signal. Okay, so what's the next step, right? So the next step is, as you can see over here, okay, as you can see over here, I'm taking this Q, right? And then the output, I'm splitting it using a splitter because I'm just interested in the Q0 bit, right? So I took the Q0 bit out, and as you can see here, this Q0 bit is also going to the Q minus 1 bit. And I'm going to explain it to why, because in the beginning, you just initialize it to 0, but afterwards, like when the loop repeats, right, the multiplication loop repeats, the Q0 bit, you're doing the arithmetic right shift, right? So the Q0 bit becomes the Q minus 1 bit. That's why I'm feeding it this Q0 bit into Q minus 1, okay? So over here, once I extract the Q0 bit, I'm using an extender circuit. What is the extender circuit? Extender circuit is just going to increase the number of bits, okay? So it takes in the input, and then, so for example, it takes in a 1-bit input and it's making a 2-bit output, okay? So if I have Q0, which is just a bit, it's going to extend it. So it's going to add a 0 and then Q0. So I'm going to have a 2-bit output, right? And then over here also, you can see that Q minus 1, I'm also extending it. So I'm also making it 2 bits, right? So that means that I'll have 0 and Q minus 1, okay? All right. And then over here, what did I do? I now left shifted, right? I now left shifted by how many bits you want to left shift you have to supply. That means that this over here, I'm going to left shift it by 1 so that I have Q0 and 0, okay? Once I do that, I can add these two inputs, right? So if I add Q0 and 0 and 0 and Q minus 1, what do I get? I get Q0, Q minus 1, okay? And this over here, Q0, Q minus 1, I'm going to put it as the select line for the multiplexer, okay? Because based on whatever is the value of Q0 and Q minus 1, as you can see here, the multiplexer has 4 input lines. One of them will be selected, and that we will have as the output of the multiplexer. All right. So now let's go and focus on the above circuit, right? This part over here. So what do I have here? Because now I need to provide this 4 input lines to the multiplexer, right? So I'm taking the M, okay, and then I'm putting it to the adder circuit, A to the adder circuit. So output, I'm going to get as A plus M, okay? And this A plus M will be selected when the select line is 0, 1, right? So 0, 1 is 1. So that means that this one, right, the second input will be A plus M, all right? And then again, similarly, you can see I'm doing A minus, right? This is M, and this is M, and this is A. So I'm doing M minus A over here a minus m over here, and then that a minus m becomes, because a minus 1 will have it when it's 1 0, and 1 0 is 2, right? So that means that it will become, since you are starting from 0 1 2 3, right? For these are the inputs for the multiplexer. So the second the line number 2 will be your a minus m. Okay, and so for 0 0, we are just going to shift. So I will just give the a directly, right? So you can see over here this a over here. So from here, I'm also taking it directly a and putting it as the input to the multiplexer, right? And similarly that a, because for a equals to 1 1 also, it'll be just input to the multiplexer without adding or subtracting. Okay, all right. So based on whatever is the value over here, if it's 0 0, this line 0 will be selected, which means that at the output I will just have a. If it's 0 1, I will have a plus m. Okay, if it's 1 0, I will have a minus 1. Okay, a minus m, sorry, not a1. Okay, and then if it's 1 1, I will just have a again over here. All right, now what am I doing is, now I'm doing the arithmetic right shift for a, and then again I have to like tell by how many bits do I want to do the arithmetic right shift. And by the way, all this circuit is already available here. Okay, I didn't create the multiplexer, I didn't create this arithmetic right shift. You can see that the multiplexer, you can find it in the plexers. So here, this is the multiplexer, you just pick it, and then you provide the input and output and the select line for it. Okay, and similarly the this arithmetic right shift. Okay, let me see where you can find it. So you can find it in the arithmetic section over here. Let me see, it doesn't have it here. So let's see where it is. The shift register. No, these are the input output. So let me see, where did I find it? Subtractor, multiplier, shifter, oh here, right? So I can just bring the shifter. So this is a logical left shift. If you want to make it logical right, you just select over here logical right and it becomes logical right. But if I need an arithmetic right, again, you have the option to choose, okay, arithmetic right, and then how many input bits it takes. Again, you can modify using this table over here, right? Once you click that thing, this table will pop up, and then you can modify the setting according to your need. All right, so this arithmetic right shift, I just got it from here. Okay, and so let me just delete that. Okay, and so what you have over here, okay, let me just pause for 1 minute. Yeah, it is arithmetic right. Okay, I was confused, like whether this is arithmetic right or I made a mistake and I used the logical right. But as you can see, I just clicked and it shows that it's arithmetic right. Okay, all right. So yeah, I arithmetic right shift, and then you tell by how many bits you are going to arithmetic right shift. For our case, we are just going to do the arithmetic right shift by 1 bit. Okay, so that's why the value will be set to 0 1. All right, so now let's see. So for the arithmetic right shift, you're just going to have the output will be the output A, right? You will shift it, and then you after shifting, whatever the value is, value will be, it will be stored back in A, right? Because that's how the algorithm works, right? So if it's a plus m, you store it back in a. If it's a minus m, you do the arithmetic right shift and put it back in a. Okay, so because of that, you will have that, right? Okay, So that you can see this A is going to go through a buffer, and I'll explain why we need a buffer over here, and then it just goes back and gets stored back in the A. Okay, so that the another round can start, right? So for another iteration, this process can continue. All right. So what happens next? Okay. So once I do the arithmetic right shift, right? My um, my A0 bit will be lost, okay? But I want to save that A0 bit. Why? Because remember, you shift A, Q, and Q minus 1 as one register, right? So if there are 4 bits in my A, that'll be A3, A2, A1, A0, and then I will have Q3, Q2, Q1, Q0, right? And then there'll be Q minus 1, right, at the end. So you are arithmetic right shifting everything, right? So what happens then? Whatever is A3, because in arithmetic right shift, you preserve the MSB bit, right? So you have A3, A3, A2, A1, right? And this A0 will go over here in the Q register, right? So you have A0, Q3, Q2, and Q1. And Q minus 1 will get your Q0, right? So this is how you will arithmetic right shift. That means that this A0, okay, we need to save somehow so that we can put it in the register Q. Okay, so that's what I'm doing here. I'm taking the A, I'm splitting the bits, and then I'm saving the A0. I'm bringing the A0 again. I'm extending it to 4 bits. Okay, so that means that when I extend it to 4 bits, I will have over here. So here I'm just getting A0, right? And over here, I will get 0, 0, 0, A0. Okay, so I'm extending it, all right? And then you can see over here, what am I doing? I'm taking the whole entire queue. And again, I am left shifting, I'm right shifting, right? And here I'm not doing the arithmetic right shift, I'm just doing the right shift because I'm doing the arithmetic in the A, right? So for this one, I'm just I'm just right shifting, okay? So that means that when I right shift, because I'm not doing arithmetic, that means over here, I'm going to get 0, Q3, Q2, and Q1, okay? And what am I doing over here? As you can see over this circuit, right? I have 0, 0, A0 over here. And now I'm again, I'm going to logical left shift, right? By how many bits? By 3 bits, 1, 1, right? So that means what do I get? I will get A0, 0, 0, 0 over here, okay? And now I'm just adding, right? I'm adding this and this, right? So when I add A0, 0, 0, and I'm adding 0, Q3, Q2, and Q1, what do I get? This is A0. I get A0, Q3, Q2, Q1. And that's exactly what I need, right? That's exactly what I need over here. As you can see, after the shifting, A0 should come in that register, right? That's why this part of the circuit is needed. All right, I hope that makes sense, and it's clear, right? Why I'm using all those components and why I'm extending the bits. All right. Okay, so let's see the rest of the circuit. Okay, so after that, again, remember, A gets stored in A after you do addition, multiplication, and shifting, addition, subtraction, and shifting, and then Q also gets stored, right? So here you can see, once you do that, okay, whatever this output, right? Because this output over here, it will be your A0, Q3, Q2, Q1. Okay, and again, this goes to the buffer, and then you can see it will go back into the queue. Okay, and this part over here is the counter. How we going to implement our counter so that it just runs for c equals to n, right? So it iterates for n times, and then the multiplication is done, and then the circuit will stop, right? This a and q does not get updated anymore. Okay, so let's see how we do that. So what did I do? I have used a counter over here. Okay, this is a counter. This is not a register. Okay, so where do we get where can you find this counter? It's again in the memory section under counter. It looks similar to the register, but it's not. Okay, so you put the counter. Okay, and then you can see if you just hover your mouse, it will tell you, okay, this input is load when loads from data input if count is 0 or decrements. Okay, this is data value that you are going to input to the counter, and this is like when this is 1, count is 1, the counter increments or decrements. Okay, and this is the output. Current value of the counter is going to be displayed over here. Okay, so since I'm implementing a 4-bit multiplier, right? So my count is going to be 4, right? So I'm going to set it to 100, but for now it's 00. But when I run the circuit, I will show you that I have to initialize these values. Okay, and also I'll have to initialize this to 1 and this to 1 so that the counter functions properly, right? And whatever is the value, output value of this counter, right? I'm going to compare it because I have to check whether the counter became 0 or not, right? So again, this is just a comparator, and this circuit is also, this component is also already available to you. Okay, so here is the comparator. So if you just pull this comparator, and you can see it will take the number preceding the comparison operation, and the second one is the number following the comparison operation. Okay, are they greater, are they equal, or is it less than? And this you can have 3 output values. All right, so you just pick that component and then see if the output of the counter matches this set value of 00. Okay, if when they match, this equal to line, right? This will be 1, right? And then what did I do? Because if the counter is 0, then we need to stop, right? We need to stop the process. We don't need to multiply anymore because we have found the result. Okay, so that's why whenever it's 1, I'm adding a NOT gate so that the output of the NOT will be 0. Okay, and whenever this NOT 0 is provided to this buffer, that means that this buffer will stop. This buffer will not it'll stop, right? So basically the input will not come out of the buffer. Okay, so this will always be 0, and this A and Q will not change. Okay, so this is how I have implemented the Booth's algorithm using the Logisim. Okay, and let's run. Okay, let's try one example. So let's say we want to multiply 3 and 2. Okay, we know the result should be 6, and we also know the result is in AQ register. Okay, so the final result will be in AQ register. Okay, so let's see how we do it. So first of all, I have to go to select the hand symbol, right? I select it to 1, and let's say M, I want to select it as I said, it's 3, right? A is initialized to 0. Again, you have to enable the enable line for this register, enable line for this register, enable line for this register. Okay, these two will also be enabled. All right, and then let me see, what else do we need? Okay, Q is going to be 2. All right, q minus 1 will be 0. It's already zeroed over there. And the counter, we have to initialize it to 4, right? So that's 4. I'm also going to set it over here as 4. Okay, what else do we need to do? All right, this has to be 1 because the multiplexer will only select the lines when we have the select line as well as this enabled. We are going to right shift by just 1 bit, so that's why I selected over here 1. All right, and then what else over here? Okay, this also we are going to just right shift it by 1. So I have enabled it as 1. This will be, we are doing the, this is left shift, sorry, and this is right shift. I'm right shifting it by 1 bit. So that's why I selected to 1. Okay, and here again, you have to set it to 1, 1 because you have to shift it by 3, right? So that your A0 becomes the MSB bit. All right, and let's see, this is 0, 0 is fine. Okay, so looks like we have done all the initialization. Yeah. Okay, so now let's run the circuit. Okay, let's run the circuit and see what result do we get. So I'm going to go to simulate. I'm going to go to ticks enabled. For anyways, I have set a frequency of 1 hertz. Okay, and if you want to make it a little bit slow, you can make it a little bit slow. Let's for now make it a little bit slow, 4 hertz. Okay, and now I'm going to go again to simulate and then ticks enable. So you see the circuit is running, right? And then it has already stopped because this is 1, means the counter has gone to 0 and it has stopped and nothing else is flowing through this data paths, right? And the result is in A, Q, as I said, A has 0, Q has 6, right? So we were multiplying 3 times 2, which is 6, and 0 and 6, you have got the result. Okay. And one thing to remember is because it's a 4-bit multiplier, right? Again, you can try out for different values, but since it's a 4-bit multiplier, the range of numbers that I can multiply will be 2 to the power 4 minus 1, right? So it'll be from minus 2 to the power 4 minus 1 to 2 to the power 4 minus 1 minus 1, since we are starting from 0, right? So that means that 2 to the minus 2 to the power 3 to 2 to the power 3 minus 1, which is 2 to 2, so it's minus 8 to 7. Okay, so you can multiply only the numbers within this range. Okay, so if you want to multiply larger numbers than this, then you have to make the multiplier with larger, like maybe 8 or 20 or 32-bit Boots multiplier, depending on what numbers you want to multiply. All right, so that's it. I hope this video was helpful to you, and I hope this Logisim implementation helps you understand the Boots algorithm in more detail. All right, thank you. Bye-bye.